what we are having in chapter 7, it should be uniform circular motion. So for uniform circular motion related to a motion that is in circular path, circular path, and we are referring to the speed only. Okay, we are not referring to the velocity yet, because we haven't really justify the direction of the circular motion, whether, like I said to you, for the circular motion and rotational motion, the direction is more or less either clockwise or counterclockwise. So we will use more of the direction in chapter 8 compared to chapter 6, chapter 7. Okay, and related to that also, okay, for the velocity that is kept constant, sorry, the speed that is kept constant, you can calculate for the centripetal acceleration and centripetal force. So for the centripetal acceleration and centripetal force, those are so much related to the velocity and also the radius of the circular path. Okay, so the greater the radius, the lower the, the higher the bigger the radius, the lower the acceleration, centripetal acceleration, and also when the acceleration is lower means the force is also lower. Okay, so the radius is also depending on whether the corner is sharp or not. Okay, so it depends on whether if the corner is very big, you don't really feel, okay, that you are driving along a corner, compared to if you driving along the roundabout or doing sharp turn like U-turn, okay, something like that. So those are where the radius is very small, and you will feel the need to control your car carefully, otherwise it won't go, okay, according to the right path that you wanna drive. Okay, and there are a few equations that you need to remember, starting from s equals to 2 pi r, okay, for the full circumference, and then velocity equals to 2 pi r over t for full period, okay, full cycle, and we have AC equals to v square over r, and also F equals to MAC. Okay, so for the application of Newton's second law, I want you to think carefully what are the forces related to the centripetal acceleration. We don't really name it as centripetal force, but the type of forces is defined by whether it is normal, tension, friction, or weight. Okay, those are the examples that we have studied so far. Okay, so this is where we stop on Monday, okay, related to the upside down roller coaster. Okay, and you, if you remember, okay, we want to find the minimum speed. So one of the examples that we did was the loop. So loop is where the case that when you have something moving in circular motion, in order to keep the circular path perfect, okay, the circular motion intact all the time, you need to have some minimum speed. So that minimum speed is what you can calculate at the very top point. Okay, so at the very top point, if for the case of roller coaster, okay, you can set our condition equals to n must be greater or equal than 0. Okay, this is supposedly, okay, 0 is the minimum value, is the limitation that it must meet. Okay, so that means if you have normal in negative, means you already fall off the track. So that means the minimum value you must have in the circular motion is when normal is greater than 0. So if you if you calculated your normal as more than 0, it could be 2, 3, 4, or any other numbers. That means the circular motion will be right on track, and you will be touching, the thing will be in touch with the surface all the time. Okay, so referring to this part, we also have another example. Okay, and I think if you guys have seen this slides, okay, related to example 6, you will find the minimum speed of the bucket for the water not to pour out. So you can actually try this in your dorm, or right now. Okay, if you have string and then you have a bottle, okay, just don't open the lid of the bottle and then put some water inside it. So when you have the cable string and then tie it to the bottle and then you swing it vertically like that, okay, you can see that when the string is pulled tight and it is in motion, okay, you can see that the water will stay in the bottle. But if you slow down, okay, you will see that there will be no longer a circular path, and if you stop or somehow you slow down, the rope will go slack. So when the rope will go slack, that means there will be no more perfect circular path, and at the very top point, it's actually, the water in the bottle can fall down. Okay, so this is also refer to this example: a bucket of water tied to the end of the rope is swung in vertical circle. So you can try that. The radius is given as 0.8. What is the minimum speed of the bucket for the water not to pour out? So in other words, for the string not to go slack. Okay, not to go slack. So what you can do from there is you
Cik,
need
terlepas
to.
kita boleh masuk budak ni depan ni.
Siapa tu?
Oh,
Okay.
Amir, you good?
So for the vertical motion here, what you need to do first, okay, your first step is always, because you are dealing with forces as well. So when you are dealing with forces and acceleration, that means your first step is find out what is your free body diagram. Second, find out where is the direction of centripetal acceleration. So with this, okay, what you can do is tension is directed downward, because again, if you look at chapter 4, tension is always directed away from the object, so it is now downward. And then the weight itself is always downward, and the direction of the centripetal acceleration is also downward, like that. Okay, so in other words, if we see the direction of the centripetal acceleration is downward, means your, what do you call it, your forces downward will be taken as positive. So starting from F equals to ma, we know that both forces are downward. Then you will have the mg plus tension equals to mv square over r. So since we want to find the minimum speed, so the condition will be the same as how you want to find the minimum speed of the roller coaster. But in this case, the thing that is contributing to the circular path or contributing to the centripetal acceleration is not normal. So what you have there is the tension. So we set our condition as tension equals to or greater than 0, and then proceed with the calculation again. You will get that the velocity must be greater than 2.8 meter per second. Okay, so this is how you calculate the minimum speed. So look at the question. The question will give you the situation. Is it related to the bikers in the loop or roller coaster, or some kind of question like this? If you are needed to calculate for the minimum speed, one of the force will be set to 0, so that you can calculate for the minimum speed. So there are two forces. You can never set the mass equals to 0, because the mass will always be there. So that's why we set the tension equals to 0, because the tension is it's the type of force that connect the bucket and also the center. Okay, so the equation is like that. Okay, rearrange carefully when you bring to the left or to the right, and then you get your answer 2.8 meter per second. Don't forget the unit. Okay, so I'm giving you 2 minutes, okay, for you to do example 7. It's related to the tension in bucket rope as well. Okay, you will calculate for the tension. I'm giving you 2 minutes to try out to find the answer. The answer for A is already in the slide, so proceed to calculate for B. So I gave you the final answer in red there, so try this out. I'm giving you 2 minutes for this.
Miss,
Yes.
I want to ask, right? I opened Ulen just now, and I saw that there was a quiz there's a quiz for circular motion.
Yes, there will be quiz for circular motion. There will be quiz right after this.
Uh,
How?
does it count in our GPA?
Yes.
Because the time remaining is like 2 hours left, right?
Again?
The time remaining. Oh wait, starts at 5 p.m.
Yeah, it will start at 5 until 6:30, I think. But you can actually finish all the question within 30 minutes, 30 to 40 minutes. So it's okay. It's just this question. I will give the question right after this. Don't worry, don't worry. I
Scare me.
hope it will be fine with you guys. Okay, don't worry. Only for chapter 7. Okay, only for chapter 7.
All right, thank you.
Okay, don't worry. I know you guys are afraid. Why are you guys so afraid? Okay, by giving you quizzes, I will help you with the marks. Okay, but you need to put your effort on it as well. So I cannot just give you extra marks or bonus mark like that. So I need to give you something like this quizzes. Even though behind my back you discuss about it, but as long as you discuss things and then related your discussion is related to physics, I'm happy enough. Okay, as long as you understand. Okay, that's my only intention anyway. Okay, so I will give you the questions right after this. Okay, all right, so back to this one. You have 3.5 kg bucket tied to the end of the rope and swung in vertical loops. So you know that in circular motion, it can be horizontal, it can also be vertical. So in this case, it's a vertical loop with radius given 0.8. Constant speed is also given 30. Okay, where you have this constant speed, we don't really care whether it is having a clockwise motion or anti-clockwise motion, so not yet. Okay, and then to calculate for the centripetal acceleration, we know that the equation is AC equals to V square over R. For this one, you already been given with the speed and you also have the radius, so you just plug in all the numbers and you will straight away get 11.25 meter per second square. So that should be your centripetal acceleration. Next, determine the tension in the rope when the bucket is at the bottom and top of the loop. So again, your first step is always justify the direction of the forces acting on the bucket. So at the top part, you have the tension going down, weight is also going down, and no other forces there. You don't have normal because it is not in touch with any surface, and you don't have surface means you don't have any friction. Okay, so that's it. You only have tension and the weight. And then you have at the bottom part, the tension is directed away from the object. So in this case, it is directed upward. And then the mass or the weight is directed downward. So to calculate at the bottom part, sorry, at the top part first. Okay, at the top of the circle, you have Ft plus mg equals to mac. So since we have centripetal acceleration to this direction, so you can say that all the forces downward will be taken as positive. Then pick Ft as your head of equation. So leave it on the left and bring everything to the right. You will see that you will have mv square over r minus mg. Proceed with the calculation. You should get 5.1 Newton. So since this calculation is using 9.81, but I'm using 9.8. I'm using 9.81. Okay, the decimal places will be a little bit different, but you leave it like that. It will be okay. Okay, just fine. Either you use 9.8 or 9.81. Okay, and then at the bottom part, you will see that Ft minus mg equals to mac. So the minus they're referring to that the tension and the weight are having different direction. Okay, so since we follow centripetal acceleration, so direction upward is taken as positive. Okay, so proceed with the calculation. Again, be careful when you are arranging the formula from left to right. You should be getting 73.7 Newton. Okay, so with this, you will see that, okay, at the top and at the bottom, okay, even though with the same speed, you will see that the tension will be different at the bottom and at the top. So you will see that at the top part, the tension is only 5, but at the bottom, the tension is 73.7. So in this case, let's say if when you are swinging, when you are making the circular motion, if this rope is going to break or disconnected, okay, or just to break, okay, it means it will most likely happen at the bottom part of the circular motion, because at this point the tension is greater than the top one. Okay, so these are the behind meaning. Okay, when you are analyzing, do not only focusing on trying to find the final answer. You need to also understand and the analysis, or what is the thing related to the calculation. So in this case, although you are calculating for the value of the tension, behind it you should see that at the top and the bottom there are there is a great difference in tension. So that means if the rope is going to break apart, that means it will be most likely happen at the bottom because the tension is so much greater there. All right. This is also example 7. So you can find more exercises or examples related to centripetal force and centripetal acceleration. Now we are going to go to fundamental forces in nature. So when we talk about fundamental forces in nature, now we want to talk about the gravity. Okay, later in semester 2 you will find out more on electromagnetism. Okay, since you guys are MAE, COE, and also CV. Okay, so I don't know about COE, but for EE, I think you need to know more on electromagnetism. This will be your area. Okay, and for applied sciences, more or less they will study more on nuclear forces. Okay, and we are going to learn about gravity in this chapter. So these are 4 fundamental forces that we have, that you don't see the medium. Okay, you don't see these are what you call as non-contact forces. It's there, but it's not there. You cannot see it, but because if a normal force of friction, you can see the mark, okay, on the floor. If related to the tension, you can see the string being pulled tight or it's being loose. Okay, so those are the effect you can see. But for gravity, you cannot really see, okay, the gravity effect on objects. So in this chapter you are going to check on the gravity. And okay, let me tell you in ahead, for the gravity or gravitational forces. Okay, gravity or gravitational forces. Normally, when we talk about gravity and gravitational forces, normally known as weight, because only in weight you will calculate for the G value. So when we talk about the gravity, normally we will use gravity as 9.81. But remember that 9.81 is only referring to the gravity pull towards the core of the Earth. Okay, so for example, Earth. Okay, right now we are living on Earth. So when we are living on Earth, it is, for example, it is on the surface of Earth like this. Our gravity is what force, that's the type of force that pull us towards the core of the Earth like that. Okay, but in this chapter, we are not only calculating for the Earth, you can also calculate for other planets. You can also calculate for moons, okay, or other planets or other stars, as long as, okay, we know the constants. So the constants are like mass of the planets or the radius of the planets. That will be helpful in the calculation. So right now, okay, we want to bring, okay, the topic of gravity a little bit wider, not only focusing on Earth, it can also be applied on other planets as well. Okay, so what is that? Okay. For the gravity, can you still see the slide? Is it okay? Still okay?
Yes, please.
Okay. For the
The slide is
gravity,
blank, right?
yes, just now it's blank. I'm sorry for that. I just switch on the power. Okay, for the gravity, or we call it as gravitational force, is one of the fundamental forces, like I explained to you just now. Okay, it is responsible for everything that happens in the universe. For example, we know that the orbiting of moons around the Earth, okay, orbiting of Earth around the Sun. So those are related by gravity of each object to each other. Okay, and gravitational forces act between all bodies in the universe and hold together planets, stars, and galaxies of stars. So I want you to also think that okay, there are the gravity is the responsible thing that act on the bodies. So between us and the Earth, okay, we are. I mean, if you can see something like this, okay, between you and the Earth will be object one, you will be object two. So gravity is the force that act on two bodies. It doesn't have to be between the human and the planets. It can be between two isolated system. So two isolated system means if the system is far away from any other planets, for example, okay, you have object A only being near to object B. So even though you don't see anything, actually object A is having a gravity pull to object B, and object B is also having a gravity pull to object A. So gravitational force is a force that hold the two things together. Okay, the two things together. And okay, we have one law related to the gravity. We call it as Newton's law of universal gravitation. So previously, I explained to you or introduced to you four types at least. Okay, at least four types of forces: normal, tension, friction, and also weight. So right now, there is another one. We call it as gravitational force. Okay, so for this gravitational force, okay, it is proposed by Isaac Newton that every object attracts any other object, and this is called gravitational force. So like I said just now, okay, it is not only between the planets, okay, it is also can be between two objects. So the magnitude of the force attracting two objects of mass m1 and m2 separated by distance r is given by this formula. Okay, we call this as gravitational force. Okay, listen here carefully. The equation is G m1 m2 over r squared. So m1 is referring to object 1, any object. M2 is referring to any object as well. So if it is in between of human and the earth, that means object 1 is human, object 2 is earth. If it is related to moon orbiting the earth, then object 1 might be moon, object 2 might be earth. Okay, it's like that. So it depends on the situation given by the question. And then r square is referring to the square distance of both objects. So what are the distance? Okay, and then make sure it must be in SI unit because all our calculations should be in SI unit. And the G is what you call as gravitational constant, and the value is 6.67 times 10 to the power of negative 11 Newton meter square per kg square. This is also, okay, please get your calculator, try to press constant 39. It should be this value. Okay, it will help you in the calculation. It will make your calculation easier. Any question?
No, not much. Wait, so the
Echo.
yeah, wait. Let me fix that for. Is there still echo now?
No.
Okay, so the only thing we need to know, the variables are the mass of 1 and 2 because the gravitational force of attraction is the same for both objects, right?
Yes.
Wait, so the concept is if there's two objects next to each other, there's an attraction force already, just like that.
Yes, correct.
Okay.
So actually between let's say, okay, this is what you are going to have next semester. If you put positive charge to negative charge, they will be attracted to each other. That is also called force. So that type of force is also referring to something like this. Okay, between two objects, there will be force acting on them. The force acted on object 1 by object 2 is the same as the force on object 2 by object 1. The magnitude of the force will be the same, but the direction will be different. That is basically your Newton's third law. Okay, Newton's third law. So the constant is constant 39. Okay, I hope you can use the calculator, but please use these only to help you calculate better, because it will be hard for you to always plug in all the number in the calculator, right? So you can instead use constant 39 for the calculation to be easy, but do not write constant in your start. Okay, do not write that constant 39. That's not the right way.
Yes,
Okay,
constant 39.
Mm.
What is that?
Yeah, please get, I mean, if you use your calculator, there will be one button is COSTONST. That is constant. I'm using this one. I don't know about your calculator. I'm using this one, Casio 570. Okay, if you press constant 39 in your calculator, that is exactly the value of this constant. So you don't need to plug in the number all the time. Okay, so try that. All right. Okay, so this is the equation for you to use. Okay, and again, it is called gravitational force. So let's try one example related to gravitational force. Read the question and find the answer.
Wait, miss, I have a question.
Mm.
So like let's say like, because these are only for two objects, so if there are three objects near each other, will the attraction force on each of them look different? Will it be like a triangle-ish thing?
Yes, that will be like that. There will be more or less two-dimension forces. That is exactly what you are going to have next semester.
Oh boy, sounds like fun.
If we meet each other again next semester, I'll try my best to explain that to you. Okay, I don't know yet whether I'll get your class or not next semester. Okay, so we have the question like this. Calculate the gravitational force acting between two objects of mass 70 tons each. So since tons is not our SI unit, what is the conversion? Anybody knows?
1,000, right?
Okay, 1,000 kg equals to 1 ton, and then the difference, so the distance between them is 200 millimeter apart. Okay, so in this case, they are far away from any planets. So when they are far away from any planets, basically they are not connected, or they are not being pulled to any gravity of any planets. So that means you are calculating for the gravitational force only between these two objects. The two objects has the same mass, okay, but the distance between them is you have to calculate twice. First, when the distance is 200 millimeters, and then the second one you recalculate when the distance is 10 times smaller. It should be 20 millimeters. So the calculation should look like this, and your answer will be like this. Okay, because the distance is reduced by 100 times, because the distance has a square, you can see that it is reduced, the force is increased by 100 times. So the answer for number one is, so the first one is 8.17 Newton. The answer for the second one is 817.1 Newton. Okay, I hope you get this number. Okay, the constant, it should be given in your exam, but if it is not given, since you are having our final exam online, okay, you can just use your internet to browse what are the values and the constants, okay, if they are not given. So be careful with the square there, and then make sure to keep everything in SI unit. Okay, so supposedly you will get this value as your answer. Okay, so that should be it for gravitational force. So right now, what I share with you so far today related to gravitational force, it's how you calculate for the magnitude of the gravitational force. But if you realize that we are actually in the chapter focusing on circular motion. So what is this gravitational force related to the circular motion? So we want to see that in a bit. Okay, it's now related to the weight. Okay, for the circular motion, I will talk about it a little bit later. So right now we focus on another another type of calculation related to the gravity. So previously we have weight related to mg. Okay, the equation is weight equals to mg, and we know that normally in our calculation right from chapter 1 until chapter 6, the gravity is always 9.81. So like I said to you just now, for the gravity itself, it's depending on the location of the object. So if the object is not on the earth, of course you need to find the value of the gravity, so depending on which planets it is located. So now we want to broaden the definition. Okay, the total gravitational force exerted on the body by all other bodies in universe is also what you justify as the weight, and the gravity, it can be calculated. Okay, when near the earth, we can neglect all other gravitational force and consider the weight as just the earth gravitational attraction, because when you have one, if this is our planet, there is certain range, okay, how far from the earth that the gravitational pull still can act on the body. Otherwise, you'll be floating somewhere around the universe because you are not connected to the gravity, earth gravity anymore. Okay, and then when the body is at the surface of the moon, for example, then we can neglect all other forces from other bodies, and the gravitational pull is only the gravity is only from the moon itself. Okay, so it depends on the planet itself. Okay, so for the gravitational force on earth, okay, listen here carefully. Okay, listen here very, very carefully. For the weight of a body of mass m, okay, now we are trying to find out what is the formula to find the gravity. Okay, so if it is on earth and it's on the surface of the earth, like us ourselves, okay, we are actually being pulled towards the core of the earth as well. So on the surface, we have from F equals to G ME M over R square. We know that, like I said to you just now, okay, it is between the two bodies, M1 and M2. So if we are talking about a body of mass M on the surface of the earth, that means right now we are talking about two objects, the object and also the earth itself. So one of the mass will be the earth, the other mass will be the object itself. So from F equals to G ME M over R square, one of the mass is the body, the other mass is the earth. Since the body is on the surface or surface of the earth and then reflected to the core of the earth, the radius will be radius of the earth. Okay, so it's like that. So since we want to find out the weight is one type of force that is being influenced by the gravity. So you will have the weight equals to mg me over r square equals to mg, because weight is equals to mg. Now force is also equals to g me m over r square. So you know that one of these are the same mass for the body, so you can cancel one on the right and one on the left. So what left there is G equals to the gravitational constant multiplied with the mass of the earth and then over the radius of the earth square. So normally the value of the mass of the earth and radius of the earth will be given. Okay, so you can plug this in your calculator right now. For example, you will find out the value is just like this, 9.8 something something, okay, but it will be rounded off to 9.81 or 9.8. This is basically agreed by all the scientists around the world. Okay, so yeah, if you want to try, okay, you can plug all this number into the calculator. You will get gravity equals to 9.81 only for the earth. Okay, but if you want to calculate for any other planets, you need to know what are the mass and radius for that particular planet. Okay, so it's just like that.
Wait, so when let's say like we're calculating, let's say like how to say, we are wait, G. Oh wait, so the big G is always a constant no matter where it is on the Earth.
Yes, correct.
I
The
see,
G
so the-
is actually
Oh,
because
I get
between the two objects, we don't know what lies in between. So those are the things might affect the calculation. So these scientists already come out with this constant, so to normalize the numbers. Okay, just
Okay,
normalize numbers.
so-
So that's why we have the constant there.
So now my question is that now that we have learned that there are two kinds of small g, like the gravitational pull, right? Like from questions from now on, are they going to continue to ask us to use 9.81, or will they sometimes like tell us that this is happening at the equator, then we're supposed to know we're supposed to use 9.78, or it's
Oh,
happening
no,
at the
no.
So-
Okay, from our calculation, normal calculation is always taken as 9.8 or 9.81. Okay, doesn't matter whether, because yeah, we know that our Earth is not a perfect sphere, but okay, it's being considered as 9.8 and 9.81 in the calculation for all type of calculation related to the gravity. So we don't really need to calculate whether the location should be in equator or at the poles. Okay, so our calculation should be 9.8 or 9.81.
I see.
Okay,
So
this
we,
one is just an additional knowledge to it.
we still continue to use 9.81 now.
Yes.
Okay, got it. Thanks, miss.
All right. Okay, now, okay, listen here carefully. Again, again, again. If you have written this down, I want you to write and highlight this part again. What you have in the box here, G equals to the gravitational constant with the mass. You see the subscription E and E here. This is referring to the Earth. But if you are calculating for the Venus, then you just change for the mass of the Venus and radius of the Venus. If you're calculating for the Mars, then you change it again for the other constants related. That should be given in the calculation. Okay, that should be given. And the unit for gravitational acceleration is ms negative 2. We call it gravity, but it's actually gravitational acceleration. That's why the value is the unit is ms negative 2. It means whatever you throw things up, because of the gravity, the object will accelerate down with that value, 9.8 or 9.81. Okay, now we want to talk about the location as well. Okay, if on the surface of the Earth, we will take that the gravity is 9.81. It's because if this is the Earth, R is from the surface towards the core of the Earth. But let's say you have a certain height from the Earth, okay, like Everest, okay, they're very quite high there, and then you also have satellites. Okay, satellites also have certain distance from the Earth, and then we know that moon also orbiting the Earth. So when moon is orbiting the Earth, you can see that moon is also having certain distance from the Earth. So how to calculate for the gravitational acceleration for this one? Okay, what you can see is R here means it's the distance between the two objects and the Earth. Okay, so the object and the Earth. So if let's say you have a satellite at a certain height from the Earth surface, you can just plug in to the equation. So instead of having only radius of the Earth is only at the surface of the Earth. But if you are at a certain height from the Earth, then add them up. Add the height in the calculation. You will have there h plus re in the square root and then make it, in the bracket and then make it square. So you will have gravity equals to constant, multiply with the mass. Okay, if it is related to Earth, then use the Earth, and then you will have the distance between the object to the core of the Earth. So the equation is not alien. You just add in the height, okay, the differences of the height from the surface of the Earth into the calculation. So mass of the Earth and radius of the Earth should be given. Again, it should be given, but if it is not, you are free to use the value written in the book, or you can find it online. So you can see there, if the height is on the surface, it is exactly 9.1. Okay, if it is at a certain height above the surface of the ground, and if the height is getting higher, then you will see that the gravity will becomes lower. So when the gravity is lower, if the distance is greater, okay, by a certain amount, that means the gravity will be very weak, and somehow it can be weightless. Okay, it can be, I mean, just like in space, it will be floating because it is not connected to any gravity anymore. Okay, so it should be like that. Okay, that should be gravity height on the Earth. Okay, and the last part of this chapter I want to share with you is related to the circular orbits. So right now,
can you go back to the slide for 1 second? I need to make some personal notes. Thank you.
all right. Are you done? Are you done?
Right, yeah, I'm done. You can move on.
Okay.
Thank you, miss.
All right, you're welcome. Okay, so the next part is right now, okay, we want to see how the gravitational force is related to circular motion. So like I said to you just now, for example, when moon is orbiting the Earth, okay, actually when moon is orbiting the Earth, at the same time Earth is orbiting the sun. So they are basically moving in their own orbits. Okay, so just talking about the moon and the Earth, for example. Okay, so when the Earth is more or less sort of being in the middle, and the moon is moving around it, okay, you can say that the moon is having a circular motion reflected to the Earth. So when the planets undergo circular motion, planets will go circular motion as they orbit around, and gravitational force is the only force contributing to the centripetal force. So look at this statement. Gravitational force is the only force contributing to the centripetal force. How is this happen? Okay, because you don't have any other forces. You don't see strings between the planets. Okay, and yeah, there's no other forces. So the only force that hold them together is what you call as gravitational force. So from the equation, you see here, okay, see here carefully. I have written this for you, but it's not in a good handwriting, but I hope you can see it. Summation of Fc equals to mac. This is basically our general equation, but since only gravitational force is acting on the planets, okay, in the motion, okay, while it is orbiting, so we put that Fg equals to mv square over r. So Fg is referring to the gravitational force, so you write it in full, it becomes G m1 m2 over r square equals to m1 v square over r. So you can see that one of these m can be cancelled, okay, if for example for the moon, okay, and then whatever left is just the mass of the planet itself, and then one of the r also can be cancelled. So what are the things normally being asked to calculate here? You can actually calculate for the speed of the circular motion. So for the speed of the circular motion, what you can see from there, rearrange carefully, cancel one of the mass. What you will have there is, if it is related to the Earth, you will have v square equals to gme over r, or you can just write it in terms of the equation. It becomes v equals to the gravitational constant multiply with the planet's mass. Okay, for example, here we have me. I could make it smaller. Okay, and subscription. Okay, write it carefully, and then it should be over. Is it over? Okay, over R, and then square root. Okay, be careful this. From test one, I think there are quite a lot of you miss the square and the square root, so I don't want that to happen again. Okay, I know I haven't give it back, but um, I'm yet to finish marking because it's quite hard to mark online. So give me some time, okay? And then to maintain the motion on an orbit of radius r from the center of the Earth, the mass need to move at a speed v on the circular path. So how to calculate for the speed of the Earth orbiting the Sun or the Moon orbiting the Earth? This is how you calculate for it, okay? And what else there? Sometimes you might need to know how much time taken to move one full cycle, and how do we know that one whole cycle is 24 hours for the Earth? So that is how we can calculate by changing velocity equals to 2 pi r over t. Then you just put these 2 pi r over t back in the equation to get your time for the calculation. So for the orbiting, okay, orbit motion or circular motion, circular orbit, normally the question can ask you things like what is the speed of the circular motion, or I mean the orbit motion, and then what is the period to finish one full cycle. So please have these two equations, okay, and then you can find a few questions related to the circular orbit in the books or in any other online resources. So yeah, that's it for orbits and circular motion. So one last question related to this chapter. Okay, I want you to calculate. Okay, this is just the notes. Okay, this is the question. I want you to calculate for the acceleration of gravity. This one is gravitational acceleration supposedly. Okay, I don't really like the equation, so just scratch this word. Okay, I don't really like the way it is written. So the question one, find the gravity on the surface of the moon. Okay, that's the question. And second, the lunar rover, that should be some kind of land rover or 4WD, okay, has a mass of 2 to 5 kg. What is its weight on the Earth and on the moon? So I want you to try to calculate for this. Okay, although I have a guide with you there is a guideline on there written in the slides. Do not look at it just yet. Okay, refer to the question, try to find your answer, and then you can compare with what's written on the slide. Okay, so 2 minutes for you. Okay, try to find this answer.
Miss,
Okay.
hello.
Yes.
I got a question. What is different formula gravitational force on Earth and gravity at a height on Earth? What is the small m in formula gravitational force on Earth?
The small m
Yeah,
referring to the object, the big M referring to the planets. If it is Earth, then
what
you
do
use the
mean
Earth. Again?
Then what's the big M?
Big M, if you are calculating for the Earth, then the big M should be the Earth mass.
Sorry, I still don't get it.
Huh?
What's the big M?
Big M should be,
What is
okay. Okay, I'm sorry for the others. Let me get back to the equation. This is it, right?
big M and small m.
Big M is Earth mass. This one. Constant mass of the Earth. Small m is a body, any body on the surface of the object. If it is you with the earth, then small m is your mass. The big M is mass of the earth. Because
If
gravitational is between the two
Earth
objects, so
and
that's why you need to have that masses. Okay, again.
So in question they will give mass of Earth lah.
Yes. Constant like mass of the earth, mass of the moon, radius of the earth, radius of the moon, they will give you that.
Oh, I see.
Is it
So
okay?
formula for height on Earth, what's the difference?
Yeah, because
with
if you have a
focus?
certain height on earth like this, if you have, like satellites, it is not on the surface of the earth. Satellite has a certain distance from the surface. So if it is at a certain distance from the surface, you just put it in. So to show that that is the whole distance from the satellite to the core of the earth.
So formula for gravity at height on Earth, the relation between satellite and Earth lah.
Yes, so related to the distance from the satellite to the center of the earth.
H is height for
From
satellite
the surface.
from the surface.
H is height from the
Between
surface. RE is already the radius of the earth.
Oh, okay.
Okay, something like this. Okay, you have, this is the earth. And then this is the satellite. H is from the satellite to the surface. This is the H. RE is from the surface to the center. So the whole distance is R plus H. Do you understand it now?
Yes.
Okay.
So ME is a constant, right?
Yes, ME is a constant.
DP big. Yeah. Okay, get it. Thank you, Miss.
Okay, you're welcome. Okay, getting back to the question again. Okay, so this is what you have for the question. First, find the gravity on the surface of the moon, because the question is related to the moon. Then you are given with the moon's mass and radius. So use this to find the gravity. So use that, you will have from G equals to GMM. So I put here small m means moon. And then Rm should be moon's radius square. Be careful with the square. Supposedly you should get 1.62 meter per second square. And then for the weight of the Land Rover, given as 225, on the moon it will be 364.5. How do you get that? Okay, it is because you are calculating for the weight should be equals to mg. Then g is 1.62 on the moon and g is 9.81 on the earth. So we just use the calculation. Okay, you don't really need to calculate for the g on the earth because it is constant 9.81. We have calculated for that. So just use g equals to 9.81 for the earth, and then you should be getting these two numbers. Okay, supposedly you will be getting these answers. Is there anybody who gotten these answers right? Am I making any mistake there?
Yeah.
You got it. Okay, congratulations. So we're done with chapter 7. Woo!
Okay.
Okay, so I'll be giving the question for for the quiz. Okay, for the quiz right after this. But do not tell any other class yet, okay? Because there is another class who haven't done this quiz with me. Okay, so you can try to do this question. Before that, let me give you the attendance first. Okay, and
Wait, Miss, is that a question?
Where?
Yeah,
No.
just-
I haven't give the question yet.
Wait, so what you're saying is that basically now that we have this question, we can like leak it to the other engineering groups?
No, you cannot do that.
Then I mean, like
Please.
you're telling us not to do it, but technically we can.
Technically, yes, but
Oh.
they will have the same session with me. So why would you do that? Don't do it.
So wait, naturally, I wouldn't want to do that in a bad nature, but I remember.
Basically, just don't do it, man. Just
No, no,
don't do it.
remember
Just
what?
don't do it for the sake of others.
No.
For
Listen,
their
listen.
understanding.
Okay,
Right.
yeah,
Remember what Mr. Barbia
get
told?
the QR code first. I'll share the question right after this. Don't fight each other. I don't know what you're doing behind my back, but I hope you guys are doing fine and also doing only good things. Okay?
I demand soup.
Miss, so we're done with class?
Yeah, we're done with class, but have this 1 hour for the quiz.
Okay.
Okay. I'm not. I mean, I don't have intention to go to chapter 8 yet. So I just want you to have more examples, and you can actually see the type of questions related to the circular motion. So having this quiz is also like asking yourself whether you understand chapter 7 or not. Okay, because chapter 8 is going to be another different level. So yeah, it's always another different level for every chapters. I understand that, but I'll try my best to try to keep the explanation simple. Okay, so is the link work?
Yes.
Okay, so please share the link to the others. You have to do this for me. Okay, for the attendance today. Okay, and then for the question, for the question is actually this. Okay, let me share with you the question first. I will share this in our WhatsApp group, but again, please promise me not to share with the others. I will
Alright,
share with the
boss.
others later, no problem. Okay, but when the time comes for them, I will share with them. But this one is only for you. Quiz 2 for circular motion, there are 4 questions. Okay, there are 4 questions, all only related to circular motion. So I want you guys to try to do the question, and please state your name, student ID, and program just like usual. Okay, our normal practice, and use PDF file only for the submission. You can only submit once, so please check before you submit, and then make sure I can see the answer. If you are using pencil, make sure to have your answer for submission in pen, because I cannot see some of the answers for test 1. So please, okay, try to help me on that, and make sure the answers can be is clear to be read. Answer all question before you submit. Make sure not to leave it as a draft. Okay, so I will share this through our WhatsApp group. Okay, so please wait a bit. I'm giving you time until 6:30, so please submit within time. All right, so that's all for today. Wait.
Wait, Miss, wait.
Yes.
If I use pencil, it's okay as long as it can be seen, right?
Yes. Okay, wait for a while. Where you are? Okay, here. Okay, let me share with you the question first. This is ME. ME, this is the question. Where is it? Okay, here. Circular motion, open. There you are. Good luck.